Good morning, good afternoon everyone, and welcome to episode 4 of this series on how to make a Web 3D infinite runner game. In this tutorial, we're going to create an infinite plane using a neat trick that relies on shaders. And we'll see that it gives us a nice workaround for making the ship move automatically along the grid. Are you ready? Then let's dive in. In the previous episode, we improved the architecture of our project and we had the game instance fully handle the initialization of the 3D scene. We also created our little spaceship using Three.js buffer geometries. Today, we're going to add a grid in our scene. This grid will allow us to feel the movement because for now this big black screen doesn't give us any indication on the current speed of our ship. So we want this grid to be infinite because we're making an infinite runner, but the problem is that of course we can't make infinite objects in 3D. The trick is to simulate movement without actually moving anything. As I said last time, what we're gonna do is use shaders to add a little animation on a basic grid and make it look like it's moving towards us, so like it's moving backwards. This way, it would be visually equivalent to a ship moving forward on this plane. But it would be much more efficient because basic shaders are quick to compute and Three.js won't have to recompute lots of position updates all the time. And we won't risk running out of grid because basically everything will be standing still. So it will just be the animation that creates the illusion of movement. Okay, so let's go back to our game.js script. Before we do anything, let's just split the initialize scene method into subfunctions because it's getting a bit long. So I'll just create a create ship and a create grid method. They both take in the scene as parameter. And I'll move the code from the initialize scene function into create ship. And I'll call the two functions passing in the scene. Okay, now, how are we going to create this infinite grid with a shader? To do this, I adapted a shader that I found in this Stack Overflow answer. So here I'll just copy it into my script. If you want to get the full code, you can check out the text version of this tutorial. I will post this snippet of code so you can copy it directly. But so yeah, let's go through this piece of code together and see how it works. The idea of this script is that we just create a simple grid with Three.js grid helper object. This constructor has a few parameters like the size of the grid plane, the number of subdivisions, and the color of the minor and major divisions. And so then we apply a specific material on this object that uses a very specific set of properties that are written in a custom shader. So we'll talk about this in a sec. Just before we dive into shaders though, I want to detail a little bit this part where we create a custom buffer attribute on our mesh. So here we're using a little utility that Three.js has, the set attribute method. And it allows you to define user data on the vertices of your mesh to have additional information. So it's a way of easily storing data that you want to access on your vertex afterwards, because by default Three.js creates some basic data for each vertex, but of course it may not contain all the info that you need for your specific algorithm. So this way you can prepare more input info for the code to come, and we'll be able to use this in our shader. So yeah, we're using this set attribute function to tell Three.js that some specific vertices in our mesh have a little movable flag. Basically, this will distinguish between the horizontal and the vertical lines so that our animation that is coded in the shader only impacts the horizontal lines of the grid, and we feel like it's moving in this one direction. And so because we stored it with the set attribute in a buffer attribute, we'll be able to access this info in our shader code later on to only move the right vertices. Okay, so let's dive into the shader now. Now, the word shader can actually refer to different things depending on the context. Here we're going to talk about shaders as the scripts that define how a specific visual thing should be rendered on screen. These visuals can be pretty much anything, ranging from the UI of your game to VFX particles, or actually just showing up the 3D objects in our scene. From our point of view as programmers, shaders are like one level more abstract than materials, in the sense that materials are using shaders. So they're a bit like instances of shaders. Your shader will define the overall behavior, and then the material will be a specific version of this shader with some specific input parameters. So basically a shader is a little piece of code that has a set of input parameters, as well as some additional implicit data, and then specific functions that tell the computer how a 3D object with a material that uses this shader should be rendered. Shaders are run on GPUs, so on the graphic cards of our computers, because they are highly parallel. The idea is that we're going to define a snippet of codes that will be run by little chunks of our scene. All will run in parallel and be completely independent, and all this info combined will result in the final image. The topic of shaders is really dense, so I will clearly not be able to dive into a lot of details. But if you want a really great intro to what shaders are and how you can use them, I really recommend you watch this series of 3 videos by Freya Halmer. She's just an incredibly good teacher, she's fun, and she gives a very comprehensive overview of the whole thing. So yeah, if you're not familiar with shaders and you want to learn more, definitely go and watch these videos. But nevertheless, I will try and quickly sum up the basics of shaders here, so that we can understand the code that we've just copied. Shaders are composed of 3 parts. You have the properties, the vertex shader, and fragment shader. The properties are also sometimes called uniforms, so they're here. And they are those user-specific input parameters that I talked about before. In our case, we have 3 user-defined input parameters. We have the speed of our ship along the z-axis, so that's the automatic fly speed. We have the size of our basic grid mesh, and we have the current time in our scene. Note that you have to define them as objects with a value key. That enables Three.js to get this info as a variable with a matching name inside the shader code afterwards. Then the vertex shader, that's what will be run on every vertex of your object's mesh. So if you have a little cube like this one, for example, the vertex shader is a piece of code that will be run for the 8 vertices in parallel. It will be the exact same code each time, but of course the input vertex is different, so we'll be able to get different results based on these differences in the input parameters. Running this vertex shader is the first phase, and so when it's done, every vertex in your mesh will have outputted something to an intermediary data structure that is sometimes called interpolators. And the reason it's called interpolators is because the next step is an invisible process that the GPU does for us, and that's to interpolate the vertex output data to get results for each pixel or fragment of the target renderer. Because if you think about it, when we look at our cube, we clearly don't have as many vertices as there are pixels in our image. If we take just this edge, for example, our vertex shader only centers data for the 2 extrema, so just those 2 points, but we don't have computed results for the pixels in between, even though we do need to show them as well, so we do need some info. The solution is to interpolate between the data points that we have, so we get a blend, so a crossfade between them, for the intermediary points. When this interpolation phase is done, we have converted our data from the 3D space at the vertex level to the 2D space at the fragment level. And so that's where the second part of the shader code comes in play. That's the fragment shader. And this fragment shader acts on fragments, so pixels of the target renderer. Usually this target is basically our screen. So You can think of this function as one that takes in per pixel data that has been interpolated from the per vertex data, and that computes the proper pixel color to show on screen for this specific pixel. Okay, so our vertex shader first gets our various inputs, that's the ones that we define in the uniforms, plus some info that is specific to the vertex it's currently working on, such as our custom movable flag or the vertex color. And so this per vertex info is passed in implicitly by Three.js. We can use it directly, or we can transfer it to the fragment shader by storing it into variables like vColor here. And so that variable is retrieved later on in the fragment shader there. Then the vertex shader's main routine applies an offset to the vertices in the mesh depending on the current time and the speed. And so that's what will create the animation. We use the grid limits to wrap the offset when it reaches the border so that it just cycles indefinitely. And so this way we get the feeling that we're on an infinite moving grid. You can see that the entire block is wrapped inside an if condition, where we check to see if the vertex has the movable attribute. This ensures that we only move the vertices that create the horizontal lines, not the ones that create the vertical lines, and so that we only have this animation along the Z direction. And at the very end of the vertex shader, we simply return the updated vertex position, so with the offset, with some matrix multiplication to convert it to the right space for GPU computation. Then our fragment shader just takes in the interpolated vertex info, and it writes the corresponding pixel color on the screen, basically using the interpolated vColor variable we passed from the vertex shader. We use vectors with 4 components because we have the 3 usual red, green and blue channels for the colors, and we also have the alpha, so that's for transparency, that is set to 1, so it's fully opaque here. If you have some transparency, then you have to do a bit more work in your shader because you have to handle how different objects will be rendered if they're behind one another. But in our case, everything is opaque, so it's way easier. Okay, we now have a basic understanding of how this shader works. It can be a bit scary at first, and it's quite different from the code that you usually do when you work in the browser, or even when you work on games. Not everyone is a technical artist and works on shaders, but overall, as Freya says in her videos, it's basically front-end at a low level. So it's about writing weird mathematical stuff and working with the GPU and sending and getting parameters to produce visual effects on your screen. So if you save this, you'll see that there is now an infinite grid in your scene, but that it's not moving. And that's because for now we're not actually updating the current time in our scene. So the shader animation is basically stuck at the initial frame, at frame 0, and it can't move. So let's create a little variable to store this time and update it. We'll create a this.time variable with an initial value of 0. Use a 3.clock. So this tool allows us to keep track of time, and it will give us the time delta between 2 calls, so we can update our this.time variable. And we'll actually do this right now. So let's go to the update function and add a new line that says this.time plus equals this.clock.getDelta. And so what this does is simply increment our time variable by a little amount. And that amount is a time delta that is computed between the last time this line was executed and the current time. Now, all we have to do is update the parameter inside of our shader using this new value. So we have to transfer it into the shader using the uniforms that we've defined. We'll do this in our updateGrid method with this.grid.material.uniforms. So that's to access our user-defined inputs. Then we do .time.value. So that's a way of accessing and setting the value of the time variable in our shader. And finally, we have equals this.time. And so if you save the script now, you'll see that the grid is animated. So once again, nothing is actually moving, but thanks to the vertex displacement that's computed by our vertex shader, we feel like the horizontal lines are coming towards us, and so we feel like we're moving forward. But because the grid itself is not moving, it will continue forever, just cycling through the animation. And so we've successfully created an infinite grid for run a game. And even if we're not actually changing the position of the ship, of the camera, or even of the grid, we've used this little trick based on shader to simulate movement. This allows us to have much more efficient code because shaders are very optimized, and it avoids asking Three.js to just recompute lots of positions all the time. Next time, however, we will be moving some objects. We'll work on spawning the obstacles and bonuses on the grid, and we'll see how to make them move consistently with the grid so that the object's movement actually matches the grid animation, and we still get this illusion of movement. So I hope you enjoyed this episode, and I'll see you soon in the next one.